Now we're going to talk about simple machines. A machine is any device that transmits or modifies force, usually by changing the force applied on an object. And so all machines are combinations or modifications of the 6 fundamental types. And you'll definitely recognize some of these as we look through them. These are called simple machines. Here's the list of them. The lever, the pulley, inclined plane, wheel and axle, wedge, and screw. This year so far, we've used inclined planes. We've also used wheel and axles and talked kind of about this, but the heavy ones that we looked at, inclined planes and wheel and axles. And we'll look at the other ones here. Here's a picture of them. And, when you're thinking about a lever, being able to apply a force on something where there's a base here, lifting something heavy, that can be helpful. The wheel and axle we have used, that's similar to the setup where we had the the connected objects, and that's a wheel and axle. Pulleys are a little bit different because you can see how they're looped around those, and so we'll look at how those are used. And then inclined planes, pushing things up inclined planes. It's another example. A wedge, splitting this like a log here, and then screws as well. So when we talk about mechanical advantage, this is a phenomenon that we see when we use pulleys. And what I show in this video is there's an example of a wheel and axle where there's a mass that's being lifted up into the air. Let's say that the mass that's being lifted up into the air, let's say it's being pulled at 5 newtons. Remember, with a wheel and axle, it's just just redirected, right? So the mechanical advantage of this is 0. This is just the being pulled through here. It's just redirected, right? Now, what you have, let's say you've got a system here where you've got a mass that's being lifted up, and then it's circled around so that as it's being pulled, you have, and you got it looped around at the bottom here. You've got a force that's applied up this way and this way. So in this case, the force is split up, so there's less force applied that is required once you have the final string coming out here. And so depending on how many you have, in this case, this is let's just do one step at a time. So let's say we have that same mass. Let's say we have a hook here. Okay, we've got our string that comes here, and let's say it hooks around, and then it loops around here and it comes out. So the force of here and here, this would be split up. There'd be 2.5 newtons here, 2.5 newtons here. And so all that would need to be pulled would be 2.5 newtons. And so with this mechanical advantage, it's split up. And then with this system that I drew at the beginning here, let's say we had even another one here, and we had another force of tension, it would be split up 3 ways. So that 5 newtons would be split up 3 ways, and so on. And then you could have 4 or 5, however many pulleys that you want. So what you may be asking is, it seems like you're getting something for nothing, right? Initially, you're pulling at 5 newtons. And then over here, you're only having to pull at 2.5. And then over here, it'd even be less. And so what we have to consider with that is, as long as there's no friction, the work out must equal the work in. So let's take a look at the same example here. Let's say we have our mass here that's being pulled over a wheel and axle like this, and let's say with 5 newtons of force, and let's say we lift this 2 meters into the air. So over here, right, we're going to be pulling with 5 newtons of force, and we're also going to be pulling 2 newtons over here, or 2 meters rather. because as this goes up 2 meters, the rope's going to go 2 meters, right? So work equals force times displacement times cosine theta. The force here, let's say 5 newtons over displacement of 2 meters. And the displacement is up here, right? And the force is up, just redirected. So cosine is 0 degrees. And we would get 10 joules or 10 newton meters, right? Okay, so let's take a look at that second example where we had that mass that's being lifted over, let's see, we got the hook here, and it's being lifted over both, loops around, and then comes out. And let's say we're pulling with 2.5 newtons, right? So each of these is 2.5, fighting the, the 5 newtons downwards. So we could put that over here too. So it turns out, let's say we end up lifting this 2 meters, right? The rope that we actually have to pull here, because it's looped around, would actually be 4 meters. So we would be pulling more rope. It would be pulling 4, and then the force that we would have at 2.5 newtons. That's because as this lifts up, this is shortening, but it's double. And as we pull, we get that. So, over here, the work that we got, out of this was 10 newtons, and the work we had to put in was 10 newtons. Over here, the work that we had coming out is also the same as the work we had coming in. So, in this case, we're lifting 5 newtons. We're still doing 10 joules of work, right? Because we're lifting this 5 newton mass into the air, 2 meters into the air. And then over here, the work that we have to put in, so the work in would be 4 meters. That would be the displacement times the force, which is 2.5 newtons. So you get 10 joules as well, or 10 newton meters. So, you're not getting, something for nothing there, because, you have to pull 4 meters. But it's nice because, you can lift things that you may not normally be able to lift. They even have examples of, pianos. You may have even seen that, pianos lifting to an apartment or something. And there's tons of pulleys. And so the mechanical advantage can be very, very high, and just takes a lot of rope to do that. So simple machines, change the direction or the magnitude of an input force. And so with a wheel and axle, it just changes direction. With the pulleys, you can change direction, and you can change how much force that you pull. And then the ratio that we get of, what we have is called the mechanical advantage, as long as there's no, friction. So mechanical advantage, force out over force in, D in over D out. So let's take a look at that last example. Force out was 5 newtons, right? In every case there, we were lifting 5 newtons. But the force that we had to put in was only 2.5, right? So 5 newtons over 2.5, we would end up getting 2, mechanical advantage of 2. So I think I said earlier, the other one, mechanical advantage was 0, is actually mechanical advantage of 1 with a wheel and axle, because we're lifting the 5 newtons, and then we're pulling with 5 newtons, so the mechanical advantage is 1 with that. And then with D, D in the case where we had the pulley with the mass down here, and then it was 2.5 newtons both. We had to pull 4 newtons, and then it only went up 2 newtons, right? So D in, what we had to do is meters rather. So 4 meters over 2 meters, mechanical advantage would be 2. And so if you added another pulley in there, and you had more forces applied coming up, you'd have a greater mechanical advantage. Okay, so let's go ahead and take a look at this example here, where we have another simple machine, which is an incline. And in this case here, pushing this into the back of a truck versus just lifting into the back of a truck. That's what we're going to look at here. So let's say that we lift, in this case here, we lift the mass in 1.2 meters to the back of the truck. That's the displacement that we have. And we have, the mass, which is 25 kilograms. So if we look at the free body diagram, if we lift at a constant velocity, the force applied and the force of gravity should be equal to each other. And we can figure out what that is. 245 newtons is the force that we use to lift the box into the air into the back of the truck. We can figure out how much work that is. And we take the force times the displacement, and we get 294 joules. So if we look at this example here where it's on an incline, let's say that as we push it here, right, we have the force of gravity going down, so we can break that into the force of gravity in y, force of gravity in x. And as we push this, let's assume no friction, and let's assume that the angle is 30 degrees. So if we look at the incline, we know that we can figure out what the hypotenuse is. We know the opposite side is 1.2 meters, and the hypotenuse is 2.4 meters. So that's how far the box is being pushed up the incline. If we do mg sine theta, which would be force of gravity in x, that's what we would be going against. That would be 122.5. So the force that we would have would be going against force of gravity in the x would be the force applied here, would be equal and opposite to the force of gravity in the x as we push it up at a constant velocity. And we get the same amount of work, right? So when we have simple machine, we'll be doing the same amount of work, but in this case, we're only having to push with 122.5 newtons. But if you notice, we had to lift 1.2 meters here, but along the incline we're only pushing 2.4 meters, and so the work is the same. It's just not as much force over a greater distance. So if we look at that mathematically, force out over force in, just like we said there, 245 newtons over 122.5, mechanical advantage of 2. Okay, so when we talk about mechanical advantage as well, it's important to look at, what happens if you do have friction, right? If the surfaces are not frictionless, we can look at the efficiency of a machine and see what's happening. So if, let's say, we take our work out and we divide that by the work in, so work out is just the objective amount that, like in the last example, lifting it into the back of the truck, that would be the work out. Work in is using the machine itself. And so if you end up having to do more work, with the work in, let's say with a pulley, or, like in that ramp there, if we're fighting friction, you're going to have a greater value for work in, and so the efficiency would be less than 1. Okay, so when we look at efficiency, we look at the work out over the work in. And let's take a look at that example where we had that the 5 Newton mass, and we had the pulley where it's being lifted, looped around, and then sent out here, and it's going up. So if we look at, this is 2.5 going up 2.5, and let's say it's being lifted here 2 meters, right? So the work out that we're getting is the force times displacement times cosine theta, which, 2.5 plus 2.5 would be 5, going up 5 times 2 would be 10 joules. So that's the work out that we're getting. Now let's say that in this case that we didn't, or that we actually had friction within the pulley system here and with the hook here. And let's say instead of pulling at 2.5 newtons, it's taking 3 newtons of force, and we pull it for 4 meters. Okay, so it's pulled for 4 meters, so we can look at the work in. Force times displacement times cosine theta.